Okay, so question 1 about CPUs. You will constantly get asked about von Neumann and Harvard, talking about what's the same about them and what's different about them. Okay, now this question basically just says describe what von Neumann is. Then there's loads of things that you can write. It says state, so remember when you've got state, you're not actually having to like go into any deep depth. You just need to give something. So for von Neumann, the standard ones, my eyes are going funny today, I do apologise about that, when I marked this I was a bit generous on you if you missed out certain words. But really, we have to say single control unit is a feature. A single, I'm not going to just write 2, I'm going to write a few down. A single ALU. Okay, so one control unit in charge of the CPU, one arithmetic and logic unit to do the adding, subtracting, the comparisons and things. Right, the other classic things is you've got a single set of buses, and the key word there each time is single, which will lead you into one of the differences with Harvard and other architectures. So we've got single address and data bus, which leads to one of the problems of von Neumann, remember, bottlenecks. Right, the other things that were defined by von Neumann when he came up with this model for a CPU was shared memory. So the data and the instructions are in the same memory. It just simplifies how we access data and instructions, because when we were building all this stuff to start with, it was complicated enough. So that leads to that problem that the control unit's got, where when it fetches something from memory, it just assumes it's an instruction, but it could actually be data. So one of the things that hackers try and do is do buffer overruns, where you run out of certain areas of memory and run into other areas of memory, which is a standard attack vector. I've done quite a lot of work on CPU design to try and minimize that, not eliminate it, but minimize it. Okay, so shared memory. So programs and data will be found in the same areas of memory. And then the other thing that sits with that is the format of data and instructions is the same. And that format is just a binary number. Okay, but it is really important when you're really talking about the control unit, the buses and the arithmetic and logic unit in von Neumann, is that you do say there's only one. Okay, anyone got any queries about that? So I was a little bit loose. If you were I know what you're saying, I gave you the mark. If it was a bit too vague, there's one other thing that I've missed. What's the other thing you could have said about a von Neumann? Think about what happens in the fetch execute cycle. What's involved? So we've got a control unit, ALU, buses. What have we not mentioned from our little CPU diagram? Pretty critical. It is an example of what? If you were to say, if I said, what is in general, what's a program counter? What would you describe it as?
Register.
Yeah. So we've got specialist registers, is the other thing you can say. It would actually be quite difficult to make a CPU without some specialist registers. But yeah. Right, okay, so moving on to the second part. They gave you a clue here as to what you should be thinking about. It said, describe one feature not part of standard von Neumann architecture. So Harvard, yes, you could talk about it, but actually they were being a bit broader. The clue was there that may improve performance? So that gave you, okay, I can't remember anything about Harvard, but what things can improve performance? Right, so one thing that can improve performance, adjustable clocks. That's quite a modern thing we've got now, you know, performance boosting and things like that, depending on temperature. Adjustable clocks, separate data and address buses for instructions, which is Harvard. Pipelining, where we keep prefetching instructions. Remember that overlap, so we can maximize execution throughput. What's a big thing? There's two main ones. So clocks is one thing that can improve performance. What's the other two easy wins that we can do for performance on a CPU? What was that? Cores, yeah, multiple cores. So effectively more than one control unit. So multiple cores, or you could say execution units. That's not going to fit. Well, it might do. What's the other thing? So we've got messing about the clocks, multiple cores. There's one more main one, but you don't get on the von Neumann. Yeah, cache. If you ever say cache, don't say, if they say give 3 things that improve performance, don't say level 1 cache, level 2 cache, and level 3 cache, because it's all the same thing. Cache. One thing that's on the MARC scheme, they've got onboard GPU. Why would an onboard GPU maybe help you execute stuff quicker? No idea? So that's that high performance instructions. So things like the floating point operations to do with maths, so cars. Some of you did say things like this. Not that one. Oh, I can't do undo on this. It's so stupid. Why has it not got undo? Remember that group of instructions. Single instruction, multiple data. So things like matrix operations. So when you're doing like maths intensive calculations, single instruction, multiple data types are a massive win, which is why graphics cards are fast, because they've got multiple little cores, the shaders and the vertex and pixel shaders, but actually it's the instructions that they can execute as well that make a difference. Something that can take 1 clock cycle on a GPU might take 2,000 clock cycles on a CPU. It's massive orders of magnitude difference. I wish you could. I wish modern games would have a CPU renderer fallback like we used to have. Before we had fancy graphics cards, and when things like the 3D effects just came out, you always used to have people that didn't have them because they were very expensive, just like they are now. So they always had to have software renderers where all the 3D had to be calculated on the CPU and actually drawn by the CPU as well. Okay, so a rasterizer. Some of it takes triangles and draws loads of triangles on the screen. And it's quite amazing. My first time I got a 3D graphics card and I switched from the software renderer to the graphics card, it was like, my lord, what is going on here? Ridiculous. And you go back to the janky software renderer and it's like, wow, never gone back to this. So it would be interesting to try and run on a fully tricked out machine without a graphics card. It'd be interesting. Bit difficult because most CPUs have got an onboard graphics card these days. Right, okay, I'll stop that one there.